Hello, my name is Stefano Lorenzini. I work at Arteris IP as Functional Safety Manager. In the following slides, we want to present some benefits and lessons learned derived from the long collaboration between Arteris IP and Samsung in designing complex system on chip based on multi-cores. Specific focus will be put on designing automotive SoC embedding AI feature to be used in functional safety application. In these slides is reported a representative automotive SoC architecture. From the top left of the block diagram, it is visible the multi-core CPU subsystem, while moving on the right, some application-specific hardware accelerator are represented together with DSP and application-specific IP. On the top right side, it is visible a machine learning cluster composed by a high number of elementary processors. Moving to the bottom side of the picture, and still from the left to the right, it is represented a fundamental component of the architecture that is the memory subsystem to access the external memory. Then it follows a high-speed wired peripheral cluster containing communication MAC like USB and Ethernet, PCI, followed by a Wi-Fi subsystem, a security subsystem, and generic I/O peripheral. Last but not the least, on the right side of the picture, it is visible the possibility for the Arteris network on chip to connect other dies or external component. As evident by the block diagram, the interconnection transporting the data information between master and slave has a central and critical role in a SoC architecture. Arteris IP has a wide offering in supporting on-chip communication thanks to scalable and configurable non-coherent and cache-coherent interconnect IPs. Main challenge for this IP is to provide an on-chip interconnects infrastructure to assure application data transport with the required level of balancing between the bandwidth and the latency. It is worth to mention that particularly critical is the access to the external DDI memory that is typically slow, power consuming, and requiring smart access scheduling to do not degrade overall SoC architecture performances. This is yet another area where Arteris IP can offer state-of-the-art solution. These slides report an overview of the major Arteris IP customers that have reached today the number of about 150 different companies, 95 of each still active. It is worth to note how all the major marketing domains are today covered by Arteris IP products. Previous collaboration with Samsung already produced meaningful success story in some of these areas, like for example, the 5G base station and the server and SSD for networking application, where AI architecture and algorithms like training and inference have been already implemented. Arteris IP has a long and proven experience in the domain of the functional safety application applied to semiconductor. Arteris was a working group member and contributor to writing the second edition released in the 2018, as well as a significant contributor to the new ISO 26262 Part 11, specifically addressing guidelines for semiconductor. Thanks to the well-established collaboration between Arteris IP and Samsung Foundry, specific benefit can be provided by Samsung to customer, like for example, the full characterization and stabilization of the Arteris IP NOC into the Samsung flow, the possibility to access highly experienced design team with strong experience with Arteris IP product and quite skilled associate architects, or the possibility to exploit the most advanced 7-nanometer node to achieve about the 30% of power saving in automotive application, while increasing significantly the cell density for each square millimeter. Proof of this effective collaboration between Samsung and Arteris IP is the successful recent tape-out of an autonomous driving chip for electric vehicle. Let's now enter more specifically in the technical challenge related to the design of automotive AI chips and comparing it to regular chip design. This slide identifies 5 different technical domains, representing 5 different challenges in the automotive AI application. All of them caused by the increased hardware and software complexity to be managed in AI application. From the left to the right, first is the power consumption that is essentially set by the increased hardware complexity and the high working frequency required by the application. The performance then required to sustain real-time complex algorithm. Then the area as a consequence of the functional complexity to be implemented. The safety as a main requirement for automotive application. And finally, the schedule of the project that tends to be affected, in the sense degraded, by the design complexity and the additional functional safety process step that must be added to the chip design cycle. Okay, let's now enter in some more specific aspect of each of those areas. Power. The large chip area dominated by the white area in the current silicon process, it increased significantly the SoC power consumption. For this reason, it became important to try mitigating such power consumption by adopting strong and aggressive clock gating techniques to switch off part of the chip when not used and reduce the node switching activity. Arteris IP support 3 different types of clock gatings that are the possibility to manually switch off entire clock domain of the chip. In this case, an external entity to the chip decide when and which clock domain to exclude. Or the possibility to let the NOC IP to dynamically switch off functionality that are not used, as well as the possibility to use third-party ADI tool to locally create clock gating implementation for better usage of the power. In the next slide, an example of power reduction schema is provided. We will see that in a few seconds. Another aspect affecting the power consumption is the off-chip access to the external DDR or HBM memories. For this reason, automotive chip architecture embedding AI functionality make usage of sophisticated on-chip memory schemes that try to maintain data on chip as much as possible, limiting the off-chip accesses to the minimum required. This schema typically rely on large usage of internal RAM, static RAM, dedicated to locally manage the traffic, like, for example, closed coupled memory and cache memories. Arteris IP offers feature in this space. It is worth to mention, for example, the capability to manage cache coherences when many cores are instantiated and many traffic threads are activated into the same chip at the same time. Also, and very important for functional safety application, ACC memory feature allow protecting such on-chip memory that, affected by silicon aging or silicon susceptibility to external event, may bit flip their content permanently or temporarily. So As a final recommendation, the combination of the 7nm silicon process offered by Samsung plus Arteris capability to integrate with SoC level power management unit give the possibility to drastically reduce the power consumption. Last but not the least, the possibility to isolate chip functionalities offer also a good option for functional safety design that need to run on the fly, logic based when the application works. This way, in fact, the isolated function can be scanned by a BASE to check for its functionality integrity without interfere with the main application. As anticipated in the previous slide, this is a concept level schema representing how a system-on-chip power management unit can control and isolate functionalities by sending appropriate command to an IP. The ARM, an ARM IP has been taken as an example here in these slides, as well as sending command, of course, also to Arteris IP network on chip. Once the ARM IP is isolated, also the portion of the NOC containing the IP is shut down, allowing saving power. Please, not like this mechanism can be useful in functional safety to permanently or temporarily exclude a faulty function from the mission critical application and apply recovery action to support failed operational system. That is one of the features more and more requested now in automotive. Let's move now to performance. AI algorithms needs to manipulate a huge number of data. This is why AI architecture need access data ranging from 512 to 8 kilobits to sustain the required high bandwidth. Unfortunately, not all the industrial standard protocol, like for example ARM, AMBA, AXI, can support this request. In this case, AXI stops to 1024. Well, Arteris IP, state-of-the-art network on chip, can instead support this type of request, assuring the best support to AI architecture. Another important aspect is represented by the latencies. This is a key requirement in AI application to sustain, for example, inference operation. In this case, in fact, new calculated coefficients required to address convolution calculation or to execute, for example, a number of MAC, shall arrive as fast as possible to the same point where they are used. So minimizing the latency become key to assure AI algorithms running in real-time environments. Similarly, in stochastic architecture, delivering the same coefficients to multiple MAC units at nearly the same time is quite critical to assure a better performance. Finally, as already anticipated, increasing the quantity of on-chip RAM minimize the throughput and maximize the throughput and minimize the latencies, reducing access to the external memory, hence increasing the overall chip performance. Area. As the transistor size greatly shrink with the process node, the wires don't follow the same rule, unfortunately. Also, the number of wires increase with the complexity of the chip, like in an AI application. So these two facts translate in a more chip area that tends to be more and more dominated by the wires. That, as a further effect, can create for plane obstruction and clock tree distribution issues. Arteris IP offers solutions to contain such array increasing, like, for example, virtual channel that allow using the same physical transportation path for different logical paths, let's say. That is, different master can share the same portion of the bus in different moment. Or source synchronous communication, that is another feature, that is a technique implemented by Arteris into the network on chip to automatically assure the locality of the data and its related clock, thanks to a resynchronization process, allowing simplifying the clock tree implementation, like, for example, shown in the picture for the clock of CD2, clock domain number 2. Also, layout routability can take benefit of this technique. Let's now step in the safety area. And let's see more closely some aspects important to manage when dealing with a complex chip. As already mentioned, on-chip RAM is exposed to fail due to silicon aging phenomena, for example, or interference with the external world. This can result in permanent or temporary bit flip of the elementary information contained into the memory. Arteris offers in its solution ACC to detect and, when possible, correct such bit flip failure. Unfortunately, user pays this functionality with a slight time degradation since this functionality typically resides on the critical path. So normally a trade-off between data correction and performance should be accepted. Another capability of the Arteris network on chip regards the possibility to create dynamic routing to work around a region of the chip that have been fused out by the silicon manufacturer because, for example, discovered not properly working during the manufacturing test. This is a quite common technique to compromise the chip size and the chip yield. The possibility to create dynamic routing can be greatly exploited also in functional safety application when a function becomes faulty during the functionality of the chip, so not usable anymore. This allows the customer to support a failed operational system that is a more and more recast feature in automotive, as already said before. Another important aspect to be addressed designing functional safety chip is the possibility to verify functional safety requirements. This can be done by using fault injection simulators, for example, because and fault injection is a time-consuming process that suffers by the increasing complexity of automotive chip. This is an important aspect to keep in mind. And this is why this process step shall be carefully managed by chip designer. For example, one of the lessons learned coming from previous customer experiences regards to analyze and understand first the safety problem, as well as its requirement and its scope before starting the fault injection. Starting fault injection in a sort of a blind mode may lead to inject or simulate not in line with the item safety needs. Also, it is recommended to address flow pipe cleaning starting the fault injection simulation in RTL and selecting qualified workload that are properly simulating the design or representing the design. An example could be to use a functional safety coverage criteria for this selection. Last but not the least, usage of formal analysis tool could help as well this process thanks to their possibility to produce results without providing a workload and its capability to automatically exclude safe faults from the problem. Safe faults are faults that can be either controlled or observed. allowing the user to avoid wasting time trying to control or observe something that could be not. These slides provide some more details regarding benefits in running the fault injection first in RTL and then in netlist, using a netlist. Some of these benefits that are particularly to say useful when facing a big design like in AI application can be summarized like this. For example, machine time reduction that could decrease from months to probably days, less licenses needed to perform the same task, or a simpler debugging to be done typically when the root cause, for example, of missing this detection is not clear, etc. So overall recommendation here is to use the RTL simulation first and then the netlist simulation to validate the result. To be noted, like this approach is supported also by the norm, of course, part 11 specifically, where it says that the fault injection can be executed at different level of abstraction, conforming to the scope, of course, and the interesting fault model to be adopted for the specific evidence to be provided. Finally, the schedule. The introduction of functional safety features require the adoption of an additional step in the chip flow that is able to support this feature both in terms of functionality and in terms of process quality. This is called the safety life cycle. This is the reason why functional safety experts shall be involved at the beginning of an SoC design and not when the RTL is closed. This is because the functional safety analysis can effectively drive, let's say, the design architecture in order to find all the safety mechanisms actually required for that specific case, avoiding to find bugs too late in the design process, maybe during the netlist fault injection, causing sometimes long step back in the design flow with impact in the time to market. Last but not the least, also the correct applicability of the safety assumption, or better said, assumption of use. It is fundamental to avoid discovering too late, when probability modification are not possible anymore, that the safety IP have been wrongly integrated into the chip. Assumption views are conditions that the IP integrator shall adopt to guarantee the achievability of the functional safety for its IP. Arteris offers description of this assumption of views into its safety manual. So, summarizing, Arteris IP and Samsung helps and provide joint value in the development of automotive SoC with embedded AI capability. Arteris IP NOC benefit can be summarized in the possibility to offer well-proven and characterized network-on-chip IP into all the Samsung process nodes, and state-of-the-art feature for best PPA and chip innovation with specific attention to AI safety features. Samsung's ASIC Foundry design team benefit can be considered deriving from the largely experienced SoC architecture team that has specific and great knowledge in using Arteris IP network on chip to implement the SoC architecture. Finally, Samsung Foundry benefit can be summarized in the possibility to access state-of-the-art 7 nanometer process node to reduce the power consumption, about 30%, and the die area of the chip, as well as proven experience, of course, in manufacturing the most advanced automotive driving chips worldwide. Thank you for the attention.